How's it going, everyone? Mr. Geyser here with Lesson 12A on equivalent representations of trigonometric functions. In this lesson here, we have 7 main skills and learning objectives where we're starting off by trying to recognize and write these trigonometric identities. Second, we want to use fundamental identities to simplify some expressions. Third, we want to prove identities analytically. Fourth, we want to evaluate trig functions using those same identities. 5, we want to apply identities for sum and different formulas. 6, we want to apply identities for multiple angles. And finally, 7, we want to solve trigonometric equations using those identities. In this lesson here, mathematical identities are two expressions that are equivalent in meaning and may be substituted for each other without losing the truth of the statement. For instance, 2 plus 5 is equal to 7, and 3 plus 4 is also equal to 7. So we can say that 2 plus 5 is equal to 3 plus 4. In trigonometric identities, we will work with expressions that can make a difficult problem easier to work with and remain equivalent. Now, in general, for all of these identities here, we're looking for you guys to memorize them and then use them to solve out different equations. For these top 6 here, for these reciprocal identities, they're pretty easy to memorize. We know that sine and cosecant tie together here, where cosecant is just the reciprocal to sine. And same thing for cosecant and sine. They're just reciprocals of each other. Same thing for cosine and secant, and same thing for tangent and cotangent. For these top 6 here, we've already memorized them since 3.9. These are pretty easy. Same thing goes for these quotient identities, where we know that tangent is just y over x, or really it's just sine of x over cosine of x. And since cotangent's the reciprocal of tangent, it's just that flip version of the fraction, where it's cosine of x over sine of x. The new things we want to introduce here are going to be these Pythagorean identities. Notice this first one here. Sine squared plus cosine squared equals 1. Remember Pythagorean, where we were trying to do x squared plus y squared equals that hypotenuse squared? Well, sine is still y, cosine is still x, and if we were to square 1 here, well, 1 squared is just 1. So for this very first identity, it should feel relatively easy to memorize, where we're just saying y squared, sine squared, plus x squared, cosine squared, is equal to 1 squared. Now, for these other 2 Pythagorean identities, in just the next slide, we're going to try and showcase how this second identity of 1 plus tangent squared is equal to secant squared really is just that very first identity divided by cosine squared. And this second one of 1 plus cotangent squared is equal to cosecant really is just that first Pythagorean identity divided by sine squared. Now, if we want to look at this even and odd identities, we want to remember that sine and cosecant, those 2 trig functions that tie together, are even, meaning that when we plug in a negative value, we should get a negative value. The same is true for tangent and cotangent. Tangent and cotangent are also even functions, but when we plug in a negative, we're going to get out a negative value. The only odd function, and it's also kind of strange, but the odd function here is going to be cosine and secant, where when we plug in a negative value, we still get out a positive value. As a reminder, sine, cosecant, tangent, cotangent, those are all even functions. Plug in a negative, get out a negative. The only weird one, the odd one out, always the odd one out, is usually cosine and secant, where we plug in a negative and we get out a positive value. In example 1, if you know the basic identities, it's really easy to derive those others. For this first problem here, in that semicircle, we're just going to bring in that information where we have the radius is equal to 1 for a unit circle, and for our cosine is going to be that x, and our sine is going to be our y here. Now remember, for Pythagorean stated that if we have x squared plus y squared, we should get this 1 squared. And as a reminder, x is just equal to cosine, and y is just equal to sine. For us in pre-calculus, we need to memorize this. If we memorize this, it's really easy to find those other identities. If we take this memorized identity, cosine squared plus sine squared equals to 1. If we divide all the terms by the same term of cosine squared, notice what falls into place. Cosine squared divided by cosine squared just gives us 1. Anything divided by itself is just 1. But sine squared divided by cosine squared actually gives us this tangent squared here. And that's one of those identities where we know tangent is equal to sine over cosine. So tangent squared is going to be equal to sine squared over cosine squared. And notice this final one here where it's 1 over cosine squared. Well, we know that 1 over cosine is just going to be secant, so this is going to be equal to secant squared. And that's one of those reciprocal identities. So now we got that second Pythagorean identity. Let's try that one more time where we just divide sine squared now. So we're bringing this equation, we're dividing each term by sine squared, and notice we have a similar situation for that first term that we did for the second term, but now it's reverse. Cosine squared divided by sine squared is one of those quotient identities to give us cosecant squared. And if we take sine squared divided by sine squared, again, anything divided by itself is just going to be equal to 1. But then finally, this last reciprocal identity of 1 over sine should give us cosecant. So 1 over sine squared is going to give us cosecant squared. For this here, the main thing we want to know is if we memorize these 3 equations, where really we're just memorizing this first equation and deriving it here, we can use these equations to help us solve for later examples. Now, in example 2, let's put this into practice. We want to try and use those quotient identities to simplify and rewrite these 2 equations. Now, for each of these problems today, we don't want to move anything across the equal sign. Rather, we're trying to solve out these left side of the equations so they match these right side of the equations. And what I mean to say is, for that left side of the equation in part A, we have cosine of beta times tangent of beta is equal to sine of beta. And we want to rewrite this left-hand side so that we can showcase it simplifying over to sine of beta. To do this, we could rewrite that tangent of beta as that quotient identity where it's sine of beta over cosine of beta. And since we have cosine in the denominator and cosine in the numerator, or really they're just multiplying each other, they kind of just cancel out, and we're just left with sine of beta is equal to sine of beta. So we know that this left side, the original left side of cosine of beta times tangent of beta, really is equivalent to sine of beta. Let's take another look at this at part B, where we have sine of x times secant of x is equal to tangent of x. So it looks a little bit weird at the start, but notice that really secant here is just 1 over cosine. And if we multiply this straight across, we then get sine over cosine. And we know that from this first example that sine over cosine is just equal to tangent. Easy. Let's take a look here at example 3 now. We want to use the idea of decompositing fractions to simplify and rewrite. What I mean by saying decompositing, not decomposition, what I mean to say by decompositing is see how this top and bottom of the fraction, the numerator and the denominator, can actually be broken up into 2 terms by separating that denominator into both of those numerator terms. Now this is only valid when there's a single term in the denominator that we're distributing into all of the terms in the numerator. Theoretically, we could do something similar where if there was multiple terms in the denominator, we'd have to have those multiple terms dividing into each of those single terms in the numerator. But really, we just want to showcase that if we have that single term in the denominator, we can almost distribute it, really it's called decompositing it, into those 2 other terms. And we can actually rewrite these terms to solve out that problem where that sine over secant can be separated into sine of x times cosecant here, and cosecant over cosecant, anything divided by itself is just equal to 1. So now we have that minus 1 term and this other minus 1 term. Well, look at this 1 over cosecant really is just equal to sine. So now that we have sine of x times sine of x, just multiply those 2 together and we get sine squared minus 1. Let's try this one more time in part B, where we have secant squared over tangent and we're trying to get secant times cosecant. Well, first, let's just try and write this first fraction as a product, where we have secant squared times 1 over tangent, just separating out that fraction. And we can actually rewrite that secant as 1 over cosine squared. And we can write this 1 over tangent as the same thing as cotangent, where it's equivalent to cosine over sine. Because 1 over tangent is just equal to cotangent, and cotangent is just equal to cosine over sine. Notice that we can now simplify out a cosine from this numerator and one of those cosines from that denominator. Well, now we just have 1 over cosine times 1 over sine, which 1 over cosine is the exact same thing as secant, and 1 over sine is the exact same thing as cosecant here. Easy. For all 4 of these here, we want to try and use those quotient and those reciprocal values to rewrite these trig problems here to try and simplify them to the best of our abilities. If we take a look here at example 4, we want to verify the identities by changing sine and cosine identities. First, in part A, we're given sine squared times secant times cosecant is equal to tangent. If we were to rewrite this just really quick, I'd like trying to showcase these red terms, these blue, and these purple terms, because it almost tells us how things are connected. Notice this little trick. See how we have sine, technically sine squared, and cosecant here? Well, we know that cosecant really is just 1 over sine. So if we're ever multiplying sine times cosecant, or cosine and secant, they're really just going to simplify each other out. So now we have sine over 1 times 1 over cosine times 1 is equal to tangent. Well, now we just multiply everything together. We just get sine over cosine times 1, which really is just tangent equals tangent. Let's try that one last time here for part B, where we're given sine times tangent plus cosine equals secant. So this is the first time where we have an addition symbol on the left-hand side of our equation here. Well, first things first, let's just rewrite it just to look at these colors here. So we have a blue kind of term on the right-hand side, and we have this red, purple, and blue term, sine, tangent, cosine on the left-hand side. Well, let's just rewrite this tangent here, trying to separate it out a little bit where you have sine over cosine. Well, now, if we kind of multiply this out a little bit, we're still left with sine squared over cosine plus cosine here. And we can't just add these terms straight across. What we need to do, let's put that underneath 1 real quick. We need to multiply that fraction by a common denominator. Well, notice we want the denominator to be cosine of x. So we can multiply this term by something that's equivalent to 1. So cosine of x times 1 is just going to be cosine of x. But if we write a very special one, something like cosine over cosine, we can actually multiply this value, which is equivalent to 1, into our term here to get cosine squared over cosine. And now that we have these 2 common denominators, we can just add them straight across to now get sine squared plus cosine squared over cosine equals secant, and we're still lost. Like, this is still not very easy to look at. But notice that this sine squared plus cosine squared was one of those Pythagorean identities, where we know this whole thing is just equivalent to the value of 1. And if this is equivalent to the value of 1, we could just rewrite this as 1 over cosine. And we know that 1 over cosine is just the reciprocal equation for secant. This is how we would go through about solving it with this Pythagorean identity. What I want you guys to try and do is spot the Pythagorean identity for this next example before it pops up. I'm curious to see if you'll spot it before we use it. In example 5, we're going to verify the identity by using that Pythagorean identity. We're given this cosine of x over 1 minus sine of x minus sine over cosine is equal to secant here. So I'm going to rewrite it real quick, basically putting it into those blues and reds here. And now we need to manipulate it a little bit where, see how we have 2 different denominators for both of these fractions? Well, if we use that butterfly method, or if we multiply this first term by that value of 1, which is equivalent to cosine over cosine, and we multiply this second term by the same value of 1, but instead we use this denominator, 1 minus sine of x, which looks something like this. We're almost multiplying the opposite term by the other term's denominator over itself. Once we have this here, we multiply everything straight across. And now we have this complicated mess of red, blues, cosines, and sines. But really, we can combine this whole top numerator of both of these fractions together to get cosine squared minus sine plus sine squared all over that cosine of x times that 1 minus sine of x, those two original denominators we started out with. Notice, we have this cosine squared and that sine squared again. I've already used that associative property to kind of rewrite those terms there, kind of bring them together. We can actually write that cosine squared plus sine squared all equal to the value of 1. And now that we have this equal to the value of 1, really the numerator is equal to 1 minus sine of x. And notice, we have 1 minus sine of x in the denominator. And we can simplify out both of those terms there. Now, since both of these terms are dividing into itself, the whole term of 1 minus sine of x divided into 1 minus sine of x, we're left with the value of 1 over cosine of x. It doesn't just cancel out and turn into 0. They're dividing into each other, so we get that 1 in the numerator divided by cosine in the denominator, where that again is just equal to that reciprocal identity, where we finally get secant equals secant here. Finally, for example 6, we're going to verify the identity using algebraic techniques to simplify this cosine of theta plus sine of theta equals 1 minus sine of theta all over cosine. So we've already rewritten it in that blue and red kind of theory. And I want you guys to observe the weird path we're going to go down to actually solve this out. First, I want to try and bring this 1 minus sine of x into the numerator on this other side here. So let's just multiply it in. Let's just multiply a thing that equals 1. So we can do that 1 minus sine of theta over 1 minus sine of theta. So now we have this in the numerator, but now we have this kind of messed up denominator here. Well, let's just FOIL that out. So we're going to multiply that 1 into those other terms. We're going to multiply this sine into those other terms here. And eventually, what we would get is 1 minus sine of theta plus sine of theta minus sine squared of theta. Well, those sine thetas just cancel each other out. It's just minus sine theta plus sine theta. They just simplify out. And we end up getting 1 minus that sine squared. Well, notice this little trick. If we bring back our Pythagorean theorem, our Pythagorean identity, we know that cosine squared plus sine squared is equal to 1. If I were to subtract sine squared from this identity, just bringing this in from nowhere, if I were to subtract that from both sides, what we really get is cosine squared is equal to 1 minus sine squared of theta. And as a side note, we could do the same thing with cosine here to get sine squared is equal to 1 minus cosine squared. But I want to take a look at this first one. Notice that this 1 minus sine squared is actually in the denominator of our fraction. And we know that it's equivalent to that cosine squared of theta. So we can just rewrite that whole equation there, or that whole expression there, as cosine squared. And now that we have that denominator as cosine squared, we can simplify a cosine from the numerator, a cosine from the denominator, and now we're finished. We get 1 minus sine over cosine is equal to 1 minus sine over cosine. Thank you very much for joining me in this lesson today, where we explored and practiced using those Pythagorean identities, those reciprocal identities, and those quotient identities for tangent and cotangent to simplify out a couple of problems. If you have any questions at all, please leave them in the comments down below, and I look forward to seeing all of you guys in class. Take care.